Welcome, everyone. Thank you again for joining us today. My name is Jessie Hansen. I'm the tech writer and content strategist here at Radiusoft. Today's talk is called Optimizing Your JSPEC Usage and will be presented by Radiusoft research scientist, Dr. Stephen Coleman. Dr. Coleman has worked in neutrino physics at Fermilab and JPark in Tokai, Japan. He studied physics at the University of Colorado and received his PhD from the College of William and Mary, working on muon neutrino oscillations in a muon neutrino beam. He's also worked on the electromagnetic focusing horns being developed for the T2K and Hyper-K experiments. So thank you for being with us, Dr. Coleman, and if you're ready to start, go ahead and take it away.
Hi, my name is Stephen Coleman. Welcome to the Optimization in JSPEC webinar. I work on several projects here at Radiusoft, and today I'm excited to tell you about optimization in JSPEC. So I'm sure we've all spent a lot of time on problems, hard problems that boil down to really just optimization. So for today, we're going to be using Nelder-Mead optimization, which is a method that's been around for a long time. It's particularly useful when combined with JSPEC because it can work in high-dimensional spaces, and it's relatively robust to data sets that might contain some step-to-step statistical noise. And so we'll see how this works with JSPEC today in the webinar. So I'm sure everyone here is aware of magnetized electron coolers and their long history. I think some of the world experts in this topic signed up for the webinar. Some of them may also be experts in beta cool. So today we're going to talk about JSPEC and some of the ways it could be used to model magnetized electron cooling in ways that are different from beta cool. JSPEC is an open source C++ package developed by Hezhang at Jefferson Lab. JSPEC is a nice framework that allows users to explore the parameter space of electron coolers, as well as the different friction force models that are out there and intrabeam scattering or IBS models. On a practical level, the problem with designing magnetized electron coolers is that the parameter space is very large and requires expert knowledge and intuition to know which inputs to manipulate in order to achieve the cooler properties that you want for your design. One way to gain this intuition is to play around with the inputs and just see what happens. And Radiusoft's Cerepo gateway, as I'm sure many of you know, wraps a GUI around the JSPEC code and makes it easy to do this, to see the effects of changes in parameters on cooling. This is also excellent for beginners just new to the field. We're working today on a fork of that code that has some unique features added in. Ones that come with one added dependency on the GNU Scientific Library, or GSL. Most of these features are available in the GUI, but I'll show some features today that are only available in the command line interface. So we'll go to the next slide here. We'll use the Parkham-Chuck friction force model today, but I'll note that we get good agreement with other friction force models that are available in beta cool, which is shown in the plot here. So this red is the friction force response in JSPEC, and blue is what you get in beta cool for an apples to apples comparison. I'll also point out that John Edelin has recorded a webinar where he demonstrates the MADX GUI in Cerepo. In JSPEC, we load in the MADX format rather than MAD8, which is used in beta cool. But we also, in JSPEC, require the file to be in the Swiss parameter or .tfs format. So let's take a look at a ring. This is the RESR ring at FAIR. Using JSPEC alone to model a cooler for this design would mean searching a parameter space manually. Manually changing magnetic field strength, number of electrons in the electron bunches and the cooling bunch, things like that. And even if you were to go through this exercise, model the existing design in our GUI, and come up with a cooler that satisfies the properties that you want, someone might come in and place a constraint on one of those parameters late in the design phase, and you'd be stuck starting all over again, searching the parameter space manually. So that's a lot of time and effort. So there are 3 steps we'd like to advertise here that are ways to build this kind of friction magnetized electron cooling cooler model that can help us overcome that kind of difficulty. So we can model the existing lattice design as to start to get a baseline to see the initial admittance behavior and admittance growth. We can use an optimization algorithm to find good cooling times. So this lets the computer turn all the knobs for us. And then we can verify those parameters in a dynamic simulation with JSPEC in the GUI. And this makes sure that we are achieving the cooling that we want, and there aren't any hidden surprises that might come up with a certain set of parameters. And you may have to iterate in these steps, but it's still a lot faster than doing things manually. So right now I'm going to navigate to JSPEC in Cerepo. So you can get there as well if you go to www.cerepo.com and click on the supported codes link at the top and scroll down to JSPEC. So I'm going to go there now. When you arrive at the JSPEC GUI within Cerepo, you're presented with a file hierarchy. So each of these files is a different simulation, different model, and there are folders where I can organize all of my different simulations. Right now I'm going to open up this RESR one here. Okay, so this is the main interface for JSPEC in our Cerepo GUI. So there are different sub-windows here that represent parameters relating to different parts of the model. So I'll go through them briefly here. We have the ion beam here in the top left. So in the case of RESR, we're going to say it's protons that are 3 GeV. These are things that are usually fixed by the design. You're not going to go achieve better cooling by changing the kinetic energy of the beamline. I've got some guesses here for the other parameters related to this ring. I found some papers that indicate it has a fairly large normalized emittance, so that's represented here in the ion beam window. Down below, we select our friction force model. Like I said, we're going with Parkham-Chuck, but you have a few other options here as well. IBS models, you can choose Martini or Bjorken-Matingwa to model the interbeam scattering. Up here, you can choose a ring from a MADX lattice TFS file. So here I've already uploaded this REXR file, but you can add your own here as well. We can also get a look at the twist parameters for that particular lattice. And now we get to the actual cooling portion of this model. So for the cooling electron beam, gamma is matched to the gamma of the ion beam. So here it's about 4 for 3 GeV protons. You can set your cooling electron bunch temperatures in EV. We're going to use a Gaussian bunch beam here that has some horizontal and vertical spatial dimensions. So 1.5 centimeters in this case, and also a bunch length, which in this case is 2 centimeters. And this bunch is composed of 10 to the 8 electrons. Then for the cooler itself, we have the length of the solenoid. So in this case, we're going to say it's 10 meters long. There's only just one cooler. We don't have a series of several coolers. And here it has a relatively weak magnetic field. It's about 390 Gauss. And the beta here for this cooler, I've taken a rough estimate from the twist parameters I just showed you before of where this cooler might be placed in the geometry of the ring. All right, so once we have all that set and we set these parameters and save them, we will get an initial rate calculation that will automatically generate down here at the bottom. This tells us what the IBS rate in each dimension is going to be, the electron cooling rate is going to be, and then the total expansion rate, which is just the sum of those two things. So we can click over here to the visualization tab, and now we can run a simulation. So I'll start this one over again here in a second, but I'm running a simulation of this behavior of the ion bunch in this cooler for an hour or 3,600 seconds. I'm going to sample this 3,600 seconds 1,000 times. This is probably a bit too coarse for general use because it's propagating forward every step about 3-4 seconds. You probably want to set your step spacing so that you're getting maybe 100 millisecond step times, but for the sake of time here, I'm just going to do a quick and dirty one. So the simulation is going to take about 45 seconds. It's stepping forward through time. Here we can see as it's stepping forward that the X and Y admittances are relatively constant. In the RMS ion beam evolution window, just to its right, we can see the cooling rates in 3 dimensions. This is total cooling rate combined with electron cooling and IBS heating. And they're on the order of, they're cooling, but it's on the order of 10 to the minus 8 seconds, which is quite a long time when you take the inverse of that to figure out the cooling time from the rate. So, okay, here we finished. We've let this run for an hour and things are relatively constant for the configuration that we're starting out from. I'll note that you can choose to plot other variables here. So we can look at the bunch length with respect to some fixed number here. This is, things are changing on the order of microns over the course of the hour. So the bunch is not being cooled very effectively with this configuration. We can also see the profile of the Parkham-Chuck friction force here plotted in micro EV per meter. So not a very strong cooler that we've designed here, at least initially. But this is going to be our starting point. So now I'll click back over to slides. This is really just a demonstration of the interface in the GUI and how you can use it. You can go back if you want to and change turn a few knobs, change the longitudinal temperature, magnetic field strength, things like that. One other thing I'll note is that this was the RMS model where we're really just propagating this bunch forward with moments. If we want a full macroparticle simulation, we can just click over here. This simulates with an ensemble of macroparticles that are normally distributed in the initial phase, but are allowed to evolve independently. And you might see some non-Gaussian distributions develop here. I'll let that start going. It takes a little bit longer, but if you need to come back to this later on in questions, it'll be ready for us. Okay. So now that we've seen how to model a system, how do we design a cooler that achieves our goals? So let's say we have been given a lattice and we are charged with finding a cooling time of, let's say, 20 minutes. Let's let an optimization algorithm turn the knobs for us to find a solution. And this is going to get into a little bit of code here. Don't try to follow every detail. We will have scripts available in our GitHub repository, and we're also working on a publication that will describe this interface in detail. So this is one of those features that's only available in the command line interface. And so to access that, you can access our browser-based Jupyter instance, which is also linked from the Cerepo homepage. If you go to cerepo.com and supported codes and scroll down to Jupyter, that will take you to our Jupyter interface. I'm not going to go there right now. First, I'll talk through how this works, and then we'll see a little bit of an example. So one of the features that we've added to JSPEC is an optimization module. So you can export from the GUI a zip file that contains everything that you will need to be able to run this in the command line interface. So you can click up on the cog in the top right near the visualization tab within the JSPEC interface and click export as zip. The zip file will contain a run.py file, and we can edit that to add the section we need for optimization. So the interface for this is really very simple, and it fits nicely into the existing interface for JSPEC. We add a new section to the bottom of this run.py file called section_optimization. And this tells it to initialize the optimizer. And here, you can define the parameters that you want to vary within the optimizer and what their central values are supposed to be. And the optimizer will take those and turn them to try to find a configuration that meets your target cooling time. So here, we define that at the bottom. This time equals 20. This is saying that we want a 20-minute cooling time. We can define the axis that we want, that we care about. So here, we want to optimize a 20-minute cooling time on the longitudinal axis. And we're starting off with some spatial dimensions of the electron bunch, magnetic field strength of 2 Tesla, and number of electrons here is in terms of 10 to the 10. So we add this section optimization. You can add as many or as few variables here as you want. If you add everything that you possibly can, it's going to take a while and you might get some nonsensical answers, but that's part of the iteration process. You can start to narrow it down as you go. Here, just as an example, we'll just do a few to see how this goes. Once you've made those changes to the run.py file, then you can run this just with simply typing in Python run.py. Your lattice file should be out of your zip file. It should be in the same working directory. If not, it might throw an error. That's just a common error if your lattice file is somewhere else. As long as it's in the working directory, it should run well. And the results are stored in a plain text file called bests.txt. Now, part of the reason that this takes a long time is that we're actually allowing this optimizer to initialize 15 different optimization runs. And for each of those optimizations runs, it's choosing new initial conditions just slightly off of the central values you defined in your section _optimization, just to make sure that we're not finding local minima, and we're able to get to a cooling configuration that satisfies the constraints. So right now, like I said, this can take a while to run. I ran one of these earlier, just that we would have a result for this particular lattice file. And this is the results of bests.txt. This took maybe an hour and a half to go through all 15 iterations. And you can see that this returns some values here that tells us, we should use a magnetic field strength of 8.5 Tesla. What could be easier than generating a solenoid with 8.5 Tesla magnetic field? We should use 15 times 10 to the 10 electrons in our bunch, and that the electron bunch should be about 15 centimeters in the longitudinal direction. Okay, so this isn't exactly magic here because we've got some values that are maybe a little bit outlandish. I don't think anyone is really considering building a magnetized electron cooler with magnetic field strength of 8 Tesla. So what can we do about that? Also within the optimization algorithm is a parameter scan interface. So using the same section _optimization definition in your run.py file, if you repeat a variable, that triggers a parameter scan. So here you can define a number of steps that you want it to take. In this case, we'll take, in this example here, 100 steps between 0 Tesla magnetic field and 2 Tesla magnetic field, or 0 and 10, or you can set your number of electrons to vary as well. So any of these parameters that are defined up here in this table on the top right are available to both the optimizer and to the parameter scan. Most of them in both the vertical and horizontal direction, or in the case of electron temperature, in the transverse and longitudinal directions. You still initialize this with this optimized cooling line at the very bottom. You run this with Python run.py. It will calculate the cooling rates for values within each of those steps, evenly distributed, and it will dump the output to a scan.txt file. It's just stored in plain text. So I've also gone ahead and done this, so we can look at this file. It's just plain text, and so for this, in this case, I generated a magnetic field scan from 100 Gauss up to 10 Tesla. And we have in these columns the cooling rate in X direction, Y direction, and Z direction. So you could go and take this and plot this in Excel if you want. You can also open up a Jupyter notebook within our Jupyter web browser interface, which I've done here. And so with just a few commands, just importing standard Python plotting libraries like matplotlib and pandas to read that comma-separated value file. We can read this file in and quickly generate a plot and see this here, which is the cooling rate is a function of magnetic field strength in both the X, Y, and Z direction. This is all generated at once with parameter scan. So even though our optimizer told us that we wanted a magnetic field strength of around 8 in the Z direction, which is the green line up here at the top, now that we've done this parameter scan, we can see, okay, we can get a cooling rate that's still pretty good if we went down to something more reasonable, something like 1 Tesla or 1 or 2 Tesla. So that the extreme value that the optimizer gave us, because it doesn't have our intuition, we're able to use our judgment and improve upon what that optimizer gives us. So we can then take those values from that bests.txt file, and we can take it to our Cerepo interface, GUI interface. We can take our RESR configuration, open it as a copy. We can give it a new name. And I've actually gone ahead and done this ahead of time, but we can then put in our optimized values into this cooler. So here I have rather a large number of electrons, magnetic field strength that it suggested, which was 8.5 Tesla or so. And now we can simulate this to see what happens. So I've already let this run, but we can see that dynamically what's happening with this longitudinal variable, that the ion bunch length that we told the optimizer to optimize for is indeed shrinking quite a bit and continues to shrink over time until it reaches some minimum. This is also reflected here in the S direction cooling rate, which is more or less the derivative. We see that the cooling actually is accelerating out to about 2,000 seconds and then more or less leveling off. So we can see that the parameters that the optimization algorithm gave us actually are doing what we want it to do. If you wanted to then look at this in a macroparticle context and run that, it's going to take a little bit longer, but this is going to allow you to examine some of the histograms of the distributions as well through time. So now I'll go back to my slides while that runs, just in case there are any questions that come up. So here I've presented to you a workflow that can help you design a magnetized electron cooler from scratch. where you can model a design or a lattice that you have in the GUI. You can use the command line interface to optimize the parameters for your specific needs. And then you can go back to the GUI and use that to verify the behavior of those parameters and make sure that they are adequate. And you can go back and forth, like I said, and iterate if any one particular variable gives you some weird answers. You can fix it. You can remove it from the optimization algorithm's selection of parameters that it can knobs that it can turn. But this is a much faster way, looking at the big picture, than turning every single knob individually and seeing what gives you the cooling time that you want. So with that, I've presented to you 3 different ways to work with JSPEC, actually. One in the Cerepo GUI, one in the command line interface, and then also within the Jupyter Notebook. That has I hope that has answered some of your questions already, but I hope that I'll be able to try my best to answer your questions from this point. Thanks for your attention.
All right, well, thank you very much, Stephen. That was a great presentation. We do have a couple questions queued up here. If any of our attendees have additional questions, please don't hesitate to use the Q&A button at the bottom of your screen, and we'll get to those as they come up in line. Our first question is, why do you have a set target time for the optimizer? Why not just let it go?
So in that example, we already saw that the optimizer wanted to give us a very strong magnetic field. It doesn't have the intuition that we have. And so if one parameter, turning one knob allows it to change the cooling time some, then it's going to turn that knob a lot. And so if we let the optimizer just try to minimize cooling time altogether, you're going to get 40 Tesla magnetic fields and things like that. And so you really need to do set a target time, something to aim for, so it doesn't overshoot what might be realistic. So that's why we set the time in the optimization algorithm to 20 minutes or 40 minutes or whatever you have.
Excellent, thank you. Our next question queued up here is, how can you be sure that the optimization algorithm finds the correct set of parameters?
So we do this reinitialization task 15 times in a loop here to try to find, start with different initial values to try to get out of any local minima. But there is no one perfect set of parameters for a cooler. So just, in it's a simple example, you could find some set of parameters that satisfies your 20-minute cooling time, and you could increase your magnetic field a tiny bit and decrease your electron density a tiny bit, and that's still going to satisfy it. So they're actually, in a sense, an infinite number of possible sets of parameters. And if you run this twice, you might not get the same answer. But the setting the target time and getting close to that, you're going to basically be on a locus of possible solutions within the highly dimensional parameter space.
Excellent, thank you for that. And then it looks like we have our final question queued up here, unless someone else wants to contribute an additional. Our last question is, are there any downsides to designing a cooler that cools too quickly?
Yeah, so if you just ramp up your electron density or your magnetic field, you can wind up with some pile up in the center, and so you wind up with some non-Gaussian distributions if you have a cooler that is too strong. So there is a bit of a balance that you're trying to strike here, finding a cooler that will cool effectively in the time that you have, say in a storage ring, and not winding up with basically a trapped set of very cold ions surrounded by a cloud of ions that are not being cooled by the cooler. So that's one reason to go back and check an optimized set of parameters, is to make sure that you're not developing these bi-Gaussian distributions.
Thank you. And we do have one more question that just landed here. A couple more questions, actually. So next one is, How do you know which force formula is best in the case of magnetized cooling?
Well,
For instance, in the case of storage ring-based electron coolers in EIC. Additional point to that question.
yes. I don't have a good answer for you there. The fact that there are many different force formulas, models that don't necessarily agree all that well tells you that the answer to that should probably be experimentally determined. That being said, our colleagues here at Radiosoft have been working on some first principles, a first principle model that should be especially relevant in terms of high gamma coolers, or high gamma rings, I should say. Because I know that the cooling strength goes as 1/gamma squared, and so the effects of cooling are diminished as you get up to higher energies within a beam. But I'm not going to pick a favorite model. I showed Parkhomchuk here because it is faster and better for demonstration purposes, but that doesn't necessarily mean that it's the best.
All right, thank you. And then I think we have our final question for today, which is, are there any other codes suitable for benchmark with JSPEC?
So Betacool is an older code that is well established, and JSPEC has been benchmarked against Betacool. Betacool does not have, for instance, this optimization feature, and it is also primarily Windows-based. It has a Windows GUI, and it also, at least in my experience, can only run single core. Our JSPEC simulation here is using OpenMP to run on multiple cores to try to speed it up. Benchmark can be quite slow on a personal desktop machine. Other than Betacool, I think I've heard of some other groups that have developed their own codes, maybe at Brookhaven, but I don't think they are publicly released, so I'm not sure about that.
All right, thank you for that. We are out of time for today, but I'd like to thank everybody for attending our latest webinar, and thank you to Dr. Stephen Coleman for doing this presentation. Please tune in with us next month. We will have Dr. Stephen Webb doing a webinar on using Jupyter in beamline simulations. Everyone who attended or registered today will also get a follow-up email with links to the slide deck that was presented, as well as the video once it's posted to our YouTube channel. You can check out the recording there. That's it for today. Thank you everybody for attending, and we will see you next time.
Thanks.